So if I give a function, let's say a mapping from a set A to B, so this mapping, so we can write it this way. There's two ways of writing this. You can also write this way, a mapping from A to B. So this is a mapping. So in somehow we are saying that we pick something in the set A. So this is set A, this is set B. So we pick a certain A in the set A, we map to a certain B in set B. So this B equal to f of A, and we can just put it this way. So f of A map to B, right? So A map to B through F. So and recall this A is the domain. A is the domain and B is the codomain. So you have to understand the difference, because when we are going to try to use these ideas to prove, you should be able to know that we are picking something in the domain or in the codomain. So it's important to know that we go from the domain to the codomain. So it maps something from the domain to the codomain. Now, how can you tell if a mapping or a transformation is a function? So a mapping, also called transformation or a function, is to know as a function, you should be able to understand the definition of a function by itself. So what is the function? So let us just look at the definition of the function. So definition of the function. So if I said let f from x to y, so this is my domain is x, the codomain is y, is a mapping or transformation from x to y. So this is the set y to y, such that every element y, so every element x in x is assigned to a unique, this is very important, it's to a unique in a unique element y in y. So we are saying that every element in x, every element in the domain is assigned to a unique element in y, and every element in x must be assigned to something in y. You have to understand this. So it must be assigned to something in y, and it must be assigned to a unique element in y. That's the key concept. So you can, this is most, you can understand this easily because you use words, so it's most easier to understand this. But if you like more mathematical notation, we can rewrite this same thing this way. So we understand that from a function, every element in x must be assigned to a unique element in y. So every element in the domain must be assigned to a unique element in the codomain, and every element in the domain must be assigned to something in the domain. Every element in the domain must be assigned to something in the codomain. So that's what you understand from here. So every element in the domain must be assigned to something in the codomain, and at the same time, every element in the domain must be assigned to a unique element in the codomain. So that's very important. So this is the general mathematical notation of that. So we said that f from x to y is a function if for all x in the domain, there exists a y in the codomain such that y equal to f of x and so this is the and for all x1 x2 in the domain, f of x1 different than f of x2 imply x1 different than x2. So this part handle the unicity, and this part handle the fact that it must exist an element. That this part handle the fact that for every element in x in the domain, there must exist a mapping in the codomain. And this part handle the fact that one element in the domain cannot map to two distinct elements in the codomain. So this second part handle that. Now let's just visualize some example, and we can tell from there that if it's a function or not a function. So let me just pick some specific example here so you can see. So example, from example, we have this representation is a function, for instance. Also, this is a function. That's a function. But if I pick something like this, also this is a function. This is a function. This is clear that this is a function because every element in x, this is the x-axis, this is the y-axis. So this x-axis, y-axis, x, and then y. So you can tell that if you pick every element, if you pick something, if I pick x in this axis, I'm just going to project it to y. You can see that a map to a unique element in y. So this is a function. Every element in x must map to a unique element in y. So the domain is going to be something close to here. This is minus infinity to plus infinity because this curve can keep going. This can go up to a certain level. And again, this the set of value of x. If you pick something in this area, you're going to see that's going to match to a unique element in y. So for this x, f of x is going to give you a certain y here. Again, if you pick a certain x here, it's going to give you a certain y value there. So every x map to a unique element in y, similar to this one. Now, if you take a look at this curve, for example, if I draw something like this, if I draw this expression, this curve, you can see that if I pick a certain x here, this is a certain, let's say this is my x. So this is the x-axis, this is the y-axis. So if I pick x here, it's going to map to two value in y. So this map to y1 and this map to y2. So you can see that f of x1 equal to y1 equal to y2, but these are different. So this is not a function because we said that they must map to a unique element in y. So this is defined from x to y. So this is the x-axis, this is the x-axis, this is the y-axis. So you can see that we say that for every element in x must map to a unique element in y. So in this case, if I pick x here, it's going to map to different value, two value of y. So we have y1 and y2, which are different. So y1 is these are different, right? We can see that they are different from here. So we have f of x1 equal to y1. We have f of x1 equal to y2, but these two are different, right? So we cannot say that this is a function. Another example of function is if you pick this mapping f from a, b, c to 0, 1. So this is still a function because if I call this my domain x, this is like my codomain y, and then I define this function this way, so such that we have f of a equal to 1, f of b equal to f of c equal to 0, you can represent this this way. So this the domain, this is the codomain, this is y, this is the codomain. In the codomain we have 0 1, and in the domain we have a b c. So what you can see here, we say that f of a1 is 1, so this map to 1, and f of b is f of c equal to f of c, so they all map to the same element here. So again, this is a function because every element in x we have a, b, and c. The first part, they all map to one element in b in y. So every element in the domain map to an element to something in the codomain. So the first part is true. So when I say the first part, I mean the first part of this. So we say that for every x in x, there must exist a y in y such that f of x equal to y. So this is true already for that. Then we have to check this part. So let me go back there. So every element in the domain map to something in the codomain. So you can see that a map to 1, b map to 0, c map to 0. So that first part is true. Now we also want to make sure that every element in the domain map to only one. Every element in the domain map to the codomain map to only one in the domain. So 0. Every element in the domain map to only one element in the codomain. So b map to 0, only one element, right? Then a map to 1, only map to one element. B map to c map to 0, only map to one element. So this is a function. It's a function. Now if you pick this example, if I define f from the set again a, b, c to 0 1, then I said that f of a equal to 1, f of a equal to 0, then it's clear that this is not going to be a function because when you have x, y, this is 0 1, this is a, b, c. We say that f of a is 1. So then we say that f of a again is 0. Now this is for sure. This is not a function because already it fell here because f of a by himself map to two elements in y. So f of a give you 0, and at the same time f of a gives you 1. So we say that every element in the domain must map to a unique element in the codomain. So this is the codomain, and this is the domain. Then so it fell here because one element in the domain mapped to two elements in the codomain, and at the same time it also fell here because we said that every element in the domain must map to something in the codomain. So this doesn't have a mapping in the codomain, so it's also fell at this level. So we have failure here. We also have failure here because b and c doesn't map to something in the codomain, which is y. Just another failure there. If you pick again this case, we have a, b, c, and then we have 1 2 3 4. Then this also we have a, b, c, then we have 1 2 3 4. Then finally we have this function. Here we have a, b, c, then here we map to 1 2 3 4. So I'm just going to draw the mapping for this map to 1, and then this map to 3. So this is just some example. Then this also map to 1. So B map to 2, C map to 3 to 2, then C also map to 3. I can tell that it's going to be a failure there. So this also this map to 2, this map to 3, then we have this mapping. So now let us see tell which one is a function, which is not, what is not a function. So I will say that this is not a function, this is not a function, because we say that every element in the domain, so this is x, y, x, y, x, y. So we say x is the domain, y is the codomain. So we have a failure at this level. We have a failure here because every element in the domain must map to something in the codomain. So this doesn't have a mapping in y, so this is not a function. In this case, it's going to fail here because we say that there's two parts. Every element in the domain must map to something in the codomain. A indeed map to something in the domain, B indeed map to something in the codomain, C indeed map to something in the codomain. But the problem is here is that B and C map to B. Yeah, the problem is B and C map to different to the same element in the codomain. So no, this should be a function, because if you look at this, example, it's the same thing as this. So this should be a function. So this should be a function. Then this is correct. Now, if I look at this last expression, also this should be a function, right? This should be a function because these two guys, they mapped B map to 1, A map to 3, C map to 3. But if I change it this way, let me just change this expression so you can see something. If I change this way, then put something like this, it's going to fail. So if I put it this way, this is not going to be a function because of this part. It's going to fail here because B map to 1 and 2. So this is not going to be a function. So this is no longer a function, right? So this is a function, this is not a function, this is not a function. So we only have one function here. Okay, so I think from here you understand the difference between how to tell if it's a function or if it's not a function. Now let us move on the next concept. And if you have this is another key definition that you have to know. We say if A and B are finite set, and then the number of function from A to B is cardinality of B to the power set of to the cardinality of A. So we say that, so if you have f from A to B, the number of function from A, what we are saying here is we are saying that the number of function that we can define from A to B is the cardinality of of B to the cardinality of A. So this can help you somewhere. We use it somehow in the future, but you have to understand this definition, so that's why I brought it here. Now I'm not giving one example here, but you understand definition, so you probably need that definition later. So what is the range of the function? So we understand what's the domain, what's the codomain, how to tell if it's if a mapping is a function or not. Now, what is the range of the function? So the range of a function is a subset of the codomain it is a set of all image of the element of A. So we say that the range of a function is a subset of the codomain. It is the set of all image of the element of A. So in this case, you're assuming that the function is defined from A to B. So when you pick something in A, you get the image in B. That's what it means. And still as a subset of all image of the element in A. And we can write it this way: the range equal a set of y prime such that y prime equal to f of x for all x in x. And we have to know that f is defined from x to y, right? So in somehow the range should be a subset of the range of this function should be a subset of this set. The range should be a subset of this set somehow. And so that's what we have for the range. We say that the range is a subset of the codomain basically, and it's a set of all the image of all the element in the domain. And there's another thing that you have to know here: the identity function. The identity function, which is noted by 1x, which is defined from x to x, is defined that by for all x we have 1 x of x equal to x. So we have this in your lecture note. That's what we call the identity function. This is the identity function. And you also have to know that. So in this slide, we discuss the range and the identity function. And we say that the range is a subset of the codomain and a set of all the image of element in the domain. That's what we get from there. Now, let us move to the compositor function. Let me see. Okay. Now, the compositor function. So if I give you two functions, f from A to B and j from B to C, the way we find the composite is this way. So let me put this set. I'm just going to put the picture so you can visualize. So we have this set A, we have the set B, then we have the set C, right? So what happened is I pick a certain A. I do f is defined from A to B, so I'm going to put this way B. So this is f of A, give me B. Then when I pick f of B, G is defined from B to C, so I'm going to get something like C. Then I say G of B give you C. The reason why, so we can see that A, the function f is defined from A to B. So f is indeed defined from A to B. This is the function f. This is f. And then G is defined from B to C. So G's go from B to C. And this is the function G, right? So the composite is what? So basically you pick something from. So the question is, how can you go from A straight to C? So in order to go from A to C, you get what we call the composite. This is J wrong F of A, right? And this is the same notation as, so this is J wrong F of A give you C. So basically I said that we go from straight from this to C. So that's the composite. And this is the same notation as, you can see that we can write J wrong F of A equal to, is the same as J of F of A, right? And in order to see that J wrong F of A is going to give you the C that we are looking for, this C is that if I replace F of A, we saw that F of A give us B. So F of A, it give us B. This give us B. Then if I say J of B, it give me C. So indeed, we go from A to C through J wrong F. So that's what we call the composite. So look at this expression with attention. You are going to understand. So I said that we have two functions here, F and J. F is defined from A to B. Then J is defined from B to C. So the function f take A in the domain, then output B, small b in the codomain, which is B. Then the function J take B in his domain, because G is defined from B to C, and output a certain C in his codomain, and we get G of B gives you C, which is indeed in the codomain of J. So we get, then we can go from straight from A to B to C through the composite, which is J wrong F of A. And I say that J wrong F of A is the same as J of F of A. As you can see here, J wrong F of A is the same as J of F of A. So this is the same thing. And what is F of A? That means whatever F of A output, you can just replace it in J. So basically this gave me B, because based on this notation, G of B, F of A give us B, which is this, though we can replace this by B. Now you can compute G of B. What's G of B? It gives us C. So this is C. So you can see that we go straight from A to C using J wrong F of A. So I think this is the key picture. If you understand this, you are good to go. And another key concept that you have to understand here is that you have to understand that the compositor function is not commutative. You cannot do that. You cannot say that J wrong F, this is different than F wrong J. This is different. Be careful. This is different. You have to understand this. They are very different. And now another trick that you have to know is, if you do J wrong F wrong H, this you can remove the parentheses across this. You can change the way the parentheses look by doing something like this, but the order of expression is still the same. This I can change it this way. I can rewrite it just like J wrong F wrong H. This is fine, right? So it's the same thing. I can change it this way, and this is correct, fully correct. But if you have if I have J wrong F wrong H, is the same. This one I can also change this to J wrong F wrong H. you can see that what happened is I just basically changed the way the parentheses look, but the order of expression is still the same. J is still the first here, F still the second, and H is still the third. So that's important also. Now and there's another function that if you say that idempotent function, F is idempotent if you compute F wrong F and it gives you the same F, in somehow if you say F wrong F of X equal to F of X, then this function is idempotent. So F is idempotent if F wrong F equal to F, and somehow we are saying that F idempotent if F wrong F of X equal to F of X. So if you compute F wrong F of X, you get the same X, you get the same as a F of X, and then you say that F is idempotent. So in order to show that the function is idempotent, what you need to do, you need to compute F wrong F of X and show that it's equal to F of X. If you can show this, then you conclude, or you can show this is the same. You conclude that the function is idempotent. That's another key concept. Now, let us see what is one-to-one function, what is onto function. So now we have one-to-one function. So by definition, a function f from A to B is one-to-one. So be careful. This notation we also use one-to-one to say that the function is one-to-one. So this is one-to-one. We can also write it one-to-one. The function is one-to-one if, again, I say that one-to-one function, you can also write one-to-one this way, this notation. So that I say the function f from A to B is one-to-one if for all A prime in A, f of A equal to f of A prime imply A equal to A prime. So or you can use this this is what I use quite often, but also you can use this notation for all A prime in A different than A prime imply f of A different than f of A prime. So these are the two definitions you can use. You can prefer to use this one. You can use this. You can use this, or you can use this. But I usually prefer to use this one. It's most easier to manipulate for me. But if you prefer this one, it's fine. So we say the function is one-to-one if for all A prime in the domain. So this is the domain. You can see that this is the domain. We have f of A equal to f of A prime imply A equal to A prime. So to prove something that to put that function is one-to-one, what we are doing is we assume this to be true. We assume this part to be true. Then we need to show that this is true. So to put that function is one-to-one, we start off by saying that f of A equal to f of A prime. Then we try to show that A equal to A prime. So let's just pick one particular example here and show how that the function is one-to-one. So if I pick, for example, this function, if I pick the function f from this set to this, such that to n we associate n plus 1 plus 3. So get familiar to this kind of notation. You can also see stuff like this: f from this set to z, that from n associate f of n equal to n plus 3. So that's the same notation. It's the same thing. So the question is to show that this function is one-to-one. So show f is one-to-one. So to show that this function is one-to-one, you write the definition first. So f is one-to-one if for all x1, x2 in in the domain so Z is the domain, f of x1 equal to f of x2 imply x1 equal to x2. So basically we are going to assume this, then try to prove this expression. So we go from the fact that this is true, we assume this to be true, then we want to show that this is also true. So if f of s1 equal to f of s2 and x1 equal to x2, then we conclude. So we go from this expression. So f of x1 equal to f of x2 imply x1 plus 3, because f was defined this way, because f of n equal to n plus 3. This implies f of x1 equal to x1 plus 3. Similarly, f of x2 is going to be x2 plus 3. So now if you say f of x1 equal to f of x2, this implies x1 plus 3 equal to x2 plus 3. Then this implies x1 equal to x2, because you can just cancel out this and then get this, right? So this is a simple proof that to show that the function is one-to-one. So again, we give you this function, we ask you to show that function is one-to-one. The function is one-to-one if for every x1, x2 in the domain, f of x1 equal to f of x2 imply x1 equal to x2. So basically you want to assume this and you want to show that this is true. So that's what we did here. We assume that f of x1 equal to f2, implying what? Because we know how to compute f of x1, which is we can compute it this way. Also f of x2 we can compute this way. So we get this equal, so we can that's why we can set this equal to this. Then from here you can just extend this, because this equality you can just remove, because the same thing here, you can just cancel out this expression, then get x1 equal to x2. So because we were able to show that x1 equal to x2, we conclude that this function is one-to-one. Now let's pick another example. How about this? Show if f is show if f and j are one-to-one, then f from j is one-to-one. So that's another example. So we want to show that if f and j are one-to-one function, then f from j is one-to-one. So to show this is this. So basically I'm just going to rephrase this. We are saying that if f and j are one-to-one, this implies f from j one-to-one. That's what it means. So what is because in implication, I said in the last video that you want to, when you want to prove that P imply q, you assume this to be true, you need to prove q. This is what you need to prove. So do you assume this to be true? This is a true fact, then you need to prove that this is true. Now, because you are doing the composite here, f from j, because the goal is to show that f from j is 1 to 1. F from j is 1 to 1 if for all x1, x2 in the domain, f from j of x1 equal to f from j of x2 imply x1 equal to x2. So in order to show that function is 1 to 1, knowing that we say that if f and j are 1 to 1, then f from j is 1 to 1. So we must show that f from j is 1 to 1, knowing that f and j are 1 to 1. So I said that to show that f from j is 1 to 1, you must show that for all x1, x2 in the domain, f from j of x1 equal to f from j of x2 imply x1 equal to x2. So we assume this to be true. We need to show this. This is what we need to show. We need to show this because it's an application. So we go from the fact that we need more slide here. Yeah, so we were trying to show that f from j is 1 to 1. So we are going to go from this fact, then try to show that x1 equal to x2. So we go from this fact. So we have f from j of x1 equal to f from j of x2. This implies f from j of x is the same as f of j of x1 equal to f of j of x2, right? Now from here, what can you do? Because we said that f was 1 to 1, right? So f was 1 to 1, that means f of if f of something, since f is 1 to 1, so look at this, we said that f is 1 to 1, then because we are trying to put this assuming that f and j are 1 to 1. If x is 1 to 1, that means f of a equal to f of b. This implies a equal to b. Similarly, if j is 1 to 1, that means j of c equal to j of d, imply c equal to d. So these are key concepts because in this case you assume that f and j are both 1 to 1. So because they are 1 to 1, this is possible. So if this is possible, that means you can think of this as a and this as a b in this function, right, in f. So think of this as a and this as a b. Because they are 1 to 1, what you can do that because this f is 1 to 1, this can bring you to j of x1 equal to j of x2, right? Because of this expression. Just I told you to think of so I said think of this as a and of this as b. So this a is here, b is here, that means a equal to b. So from this, because j is f is 1 to 1, you can write this expression this way, right? And again, from this, if you think of this as a c and think of this as a d, from there you can write this also, right? So this gives you x1 equal to x2 and the proof is complete. And this is true because of this, because j is 1 to 1. So you get the point. So I'm just going to erase this part. So this is since because f is 1 to 1, then you can write this. Then from here, because to go to this, because j is 1 to 1. So that's what we have for that. So again, so we say that show that if x and j are one-to-one function, then f round j is one-to-one. If x and j are one-to-one, this implies f round j is one-to-one. So this is what we have to show basically. So we assume that if these are one-to-one, then we have this. So in order to show something like this, it's like a P imply Q. I said that we assume P to be true. We want to show that Q is true. That's what we did here. So we said that we want to show that f round j is one-to-one. And by definition, f round j is one-to-one if f round j of x1 equal to f round j of x2 imply x1 equal to x2. So again, we assume this to be a true fact. So we are going to assume this to be a true fact. Then we are trying to prove that this is true. This is what we need to show. So we assume this to be true. We try to show that this is true. And we go from here. I said that because we assume this to be true, we're just going to use this. We have f round j of x1 equal to f round j of x2. This implies we can extend this. It's the same as f of j of x1 equal to f of j of x2. We get this. And because f is one-to-one, and as explained, you can write that this is going to be equal to this, and we have it here. Then from this, because j is also one-to-one, we can go from this expression to the final conclusion. So therefore, we conclude that f round j is also one-to-one. Then for the, I'm just going to pick another example, for example, to show that the things so this is another example. If I ask you to show that f from the domain to the codomain to x give you 5x plus 3. So you are going, sometime you're going to say f from the domain to the codomain f of x equal to 5x plus 3. You can see stuff like this. So I'm just using different notation so you can see. So it's the same thing as what I wrote down out there. So show that f of is one-to-one. So again, f is one-to-one if for all x1, x2 in Z, this is the domain, f of x1 equal to f of x2 imply x1 equal to x2. So we go from this, fact, then we try to show this. So f of x1 equal to f of x2, this imply 5x1 plus 3 equal to 5x2 plus 3, and then this imply 5x1 equal to 5x2, and then we can simplify the 5. This imply x1 equal to x2. Then when we get this, because we was able to show that f of x1 equal to f2 of x2, we can conclude that the function is one-to-one. So this is x2. My handwriting is not good. So this is imply x1 equal to x2. So, and then we can conclude that because we started off here, we were able to show that x1 equal to x2, therefore the function is one-to-one. Now, if I pick for the onto function, let me just pick another set here that we have to, another function that we have to show. So let me show again this one for the one-to-one function again. If you have f, if you have let f from x to y, then we said f is one-to-one. Then we say that for all a1 a2 subset of x. I'm going to write it down here. So for all a1 a2 subset of x, so subset of the domain, we have f of a1 minus a2 union a2 minus a1 is a subset of f of a1 minus f of a2 union f of a2 minus f of a1. So that's another function. We said that if f is 1 to 1 and a1 and a2 are subset of the domain, which is x, so this is the domain x, then f of a1 minus a2 union a2 minus a1 is a subset of f of a1 minus f of a2 union f of a2 minus f of a1. So that's what we have to prove. So you need to show that this is true, knowing that f is 1 to 1. Now, like we did in the previous chapter, in order to show that this is true, we must pick something in this set and show that it belongs to this part. So you must pick something in this set, this part, then show that it's a part of this set, right? So that's what we need to show. So let us just show that how to show it. So again, I said that we pick something in this set. We pick something in this set. We must show that the same element that we pick in this set is also in this set, right? So if you can show that, we conclude that that function is that this set is a subset. We conclude that this is a subset of this. So let y in f of a1 minus a2. Let me just use the dark color. I think it's easier. Let y in f of a1 minus a2 union a2 minus a1. If y is in this set, that means so first we pick y in this set. I'm going to give you one definition here that I should give you initially before we even start. So if you have f of a, so when you have a set a, when you have a function f from x to y, and a is a subset of x, so f of a is a set of f of a such that a is in a. This is very, very, very important concept here, because that's what we are going to use here. So look at this. So I said that if f is defined from x to y, then a is a subset of x, which is, so a is a subset of the domain. F of a is a set of f of a such that a is in a, right? So we are going to see how to use this here. We are going to use that trick at this level to show to extend, because if you don't know this, you're going to get stuck here. So look at this definition very well, and then I'm going to erase it, then we can write whatever you have there. So just by looking at what we have down here, so this is going to give us this imply. From here we can write that there must exist a certain a in a1 minus a2 union a2 minus a1 such that f of A equal to Y. So when you look at this set, when I wrote this set, this is like a f of A is like my Y here. This is like a Y because Y is in this set. This is a set of f of A. So Y is part of this set, and Y equal to f of A. So Y equal to f of A because A is part of the subset of that set. So based on this definition, Y is my f of A, which is a half here, and A must be in A. And from here, because we have Y in the f of the union, so that means there must exist a certain A in that set such that f of A equal to Y. So you understand why we went from this expression, the top to this down, using this definition, basically using this. So now I can erase this. I was just trying to explain you why we can go from this to this. So we erase this expression, so we can continue our proof. So from here, we just extend it using the simple definition. This implies A is in A minus 1 or A is in A2 minus A1, right? We just extend it. We saw that how to handle that's the definition of the union. So from here we get that's what we saw for the definition of the union on the previous chapter. So from there we can say that A is in A1 and A is not in A2 or A is in A2 and A is not in A1, right? We just extend this. We saw this definition in the previous chapter. So from here we get, because we say that from here, what was A? What was f of A was Y, right? So from here we have f of A is Y. So look at this, f of A is Y. So that means we can just replace this by, because it's a one-to-one function, we can change this to, I'm just going to put f of A is in A1, f of A is in f of A1. So apply the function f on both sides, and f of A is not in f of A2 or f of A is in f of A2 and f of A is not in f of A1. So just apply the f on this side, and then on this you get whatever you have here. So I'm just going to report that expression there. So this we get so basically the last expression was f of A is in f of A1 and f of A is not in f of A2 or f of A is in f of A2 or f of A is not in f of A1. Now, if f of A is in f of A1, so is f of A is in f of A1 and is not in f of A2, that means f of A is in f of A1 minus f of A2, right? We saw this in the previous chapter. That's the definition for A minus B. If it's not in A, if it's in A, it should not be in B. That's why from this step we can get up to this. From this we can go to here. So we get this expression, and then we have the or in the middle, or f of A is in f of A2 minus f of A1, right? And because this is the difference, what is f of A? We saw that based on how we started, f of A was y, right? So f of A was y. So we go back here, we replace f of A by y. That means y is in f of A1 minus f of A2, and or y is in f of A2 minus f of A1, right? The reason why we put the y, because back here we said that f of A was equal to y. So we get this expression because y is the same y that we have here. That means y is indeed in f of A1 minus f of A2 union f of A2 minus f of A1, and the proof is complete. So we prove our proof is complete. So let me go back and then explain again. So the goal is to show that if f is 1 to 1, we want to show that if A1 and A2 are subset of x, f of, we have this expression. So we want to show that this is a subset of all this, right? So to show that this is a subset of this, we must pick something in this set, then show that it's also part of this set. So that's what we did, and we said that let y is in this set. We want to show that y is on the other part, right? So if y is in this set, based on how I explain you, that means there must exist a certain A in the set that is inside. So the set that is inside is this part. There must be a certain A in that set, what you have inside here, in this set, such that f of A equal to y, right? So A is in that set. So because there exists, we can say that clearly that A is in that set. So A is in this set. That's why you can write this down. Because A is in this set, we can write this down. Then we can extend this. We just extend this using definition of the difference of the set. Then from here, we can apply the f function on both sides of every element. So apply f here, f here, f here, f here, f here. And we can do so because the function is 1 to 1. So I basically have f of A is in f of A1, and f of A is in f of A2, f of A is in f of A1, A2, and then this is A2, and f of A is in f of A1. So basically I just copy what we have here. So from there we can just extend it, then get what we have here, because f of A is in f of A1 and it's not in f of A2, so it can be in the difference. The same thing here, f of A is in f of A1 and it's not in f of A2, so it can be in the difference. So we just write it using the difference of set. Then from there, f of A is y. Everywhere we have f of A replaced by y, so we get this expression. So from there we can extend it, then get this final expression, and this conclude our proof. So I think this is going to help you on your homework, so you have to try to visualize that. So we are done for the one-to-one stuff. Now what we can take a look at one expression, or what is the onto function. And what do I have for the onto function? So now I think that you are able, you can clearly show that the function is a one-to-one, and also we also saw some example on how to prove that the one-to-one expression. So now, what is the onto function? So onto function. So a function is onto. So a function, let me just call f from x to y is onto if. So it's the function is onto if what? If for every y in the codomain in y, there exists a certain x in the domain such that f of x equal to y. So again, there's two things that you have to see here. So this is the domain, this is the codomain, right? You say that f from x to y is onto if for every, this is very important, for every y in the domain. So for every element in the domain, the codomain, there must exist something in the domain such that f of x equal to y. So if something is not, if you have some element in the codomain and they don't have an antecedent in the domain, it's not going to be onto. So for example, if you click if I pick first, I'm going to give an example on how to show that this function is onto. So let's consider the function f. Let's consider the function f. Show that f from this set of integers to the set of integers which from x associate x plus 3, show that f is onto, right? So we say that f is onto if for every y in z. So this is the codomain. This is a codomain. There exists a certain x in the domain. So there's a certain x, let me just put here. There's a certain x in the domain such that f of x equal to y. So basically, there are two observations here. So we say that f is onto if for every y in z, which is the codomain, because the reason why I'm specifying this, because it's not always going to be the same thing here. You can have maybe z and the set of real number, or n and the set of real number. So this can change. The reason why I'm putting this so that you can understand that the y must be in the codomain and the x must be in the domain. So in somehow, because we said that for every y in z codomain, there must exist a certain x in the domain such that f of x equal to y. So the key trick of this is what is to tell that the function is onto. What you're going to do is basically you're trying to solve f of x equal to y for x and check if x is in the domain. So basically what I'm saying here is this. So the key trick is to solve f of x equal to y for x. So when you find the x, you want to make sure that check if x is in the domain. So if x is in the domain, then you can conclude that that function is onto. But if x is not in the domain, it's not going to be onto. In that case, you have to find the counterexample of true. To show that it's not onto, you don't show it, but you have to find the counterexample, something that fell. So we are going to see how to show that it's not onto, but in this case this function is onto. We are going to see how to show that it's onto. So I say that to show that it's onto, you basically set f of x equal to y. You solve for x, knowing that y is in the codomain. You want to make sure that x is also in the codomain. So let us show that. So f of x equal to well, our function was x plus 3. X plus 3 is onto if there exists a certain x in the domain such that f of x equal to y, and y should be in the codomain. So I said that f of x equal to y. This implies, I said that we solve this for x. This implies x plus 3 equal to y, because f of x is this expression. This implied then that x equal to y minus 3. So I get x, which is this. Now how to make sure that x is in the domain? Indeed, our domain here is a set of integers. So what I do is y is in the set of integer. This implies y minus 3, because 3 is an integer, it should be in the set of integer, right? It should be in this set, should be an integer. So this implies x is in an integer, right? So x is an integer, therefore f is 1 to 1. So that was how to proceed on this expression. So give me 1 second. I have to connect my tablet, and it's kind of low on battery. Just give me 1 second, please. Okay, so now from this you know how to show that this function is 1 to 1. You know how to show this function is onto. So I said that to show this function is onto, you have to show that for every y in the codomain there must exist a certain x in the domain such that f of x equal to y. So to do that is basically, as I said, you solve f of x equal to y for x. So basically you're trying to look for x, and that's what we did here. We want to show that this function is onto if for every x in the domain there must exist a certain no, this is the opposite. So this is onto if for, did I wrote it correctly here? Yeah, so I did the mistake here. So this is onto if for every y in the codomain there must exist a certain x in the domain such that f of x equal to y. So that's what we have, and what we do is you solve f of x equal to y for x. So basically I says f of x equal to y, this implies x plus 3 equal to y, then I solve for x. So this is my x that I got from there. But because we said that y was in the set of integers which is in the codomain, so y is in the codomain, this implies y minus 3 is going to be in the domain, because y is an integer. Integer minus integer, 3 is an integer, give you an integer which indeed is in the codomain. So x is indeed in the codomain, so therefore f is 1 to 1. So this is in the codomain, in the domain, so we can say that f is onto. Now let us look at one case. So again we need to pick one case to show that it's not onto. So show that so to show that this function is not onto, what you do, you just pick a counter example. For example, if I pick the function what example is simple. So this, if I go back to this expression, it seems like this function is not this function is not this function is not onto, because if you pick y equal to 0, for example, so this is not going to be onto. This function is not going to be onto. This function is not going to be onto. So you have to recheck this. This is not onto. The reason is, so this function is not onto. This is not onto. The reason is, if you pick y equal to 0, you are not going to have something in the domain such that it map to 0 basically. So this is not onto. If you pick so f, again, that was a mistake there. So if you pick f, if you pick f of x equal to 5x plus 3, so I think this function is not onto, because if you pick y equal to if you pick y equal to 0, this is not going to work, because if you have a 0 equal to 3 plus 5x, you're going to get negative 3 equal to 5 x, so you're going to get x equal to negative 3 over 5. So this is not an integer, right? So this is not in the set of integers. So this function, what we did here, just forget about what we did here. So this function is not onto. This is not onto, because the definition of onto is said that for every y in the set in the codomain, there must exist a certain x in the domain such that f of x equal to y. But what we just realized here is if you pick this for the same function, if you pick y equal to 0, so y indeed 0 is in the codomain, so this is in the set of integers. But if you try to solve for x, you have 0 equal to 3 plus 5x. This implies negative 3 equal to 5x. This implies x equal to negative 3 over 5. And you can see that this is not an integer, so that concludes that this function is not one-to-one. It's not onto. So this is not onto. So that function is not onto. You have to be careful on this. It's not onto. And we find a counterexample. So the only way to show that the function is not onto, you find something that's going to make that fail. If you pick y equal to 0, you get x equal to negative 3 over 5, which is not an integer. So this function is not onto. That's one way to show that the function is not onto. You find a counterexample. And for counterexample also, if you pick the function f from the set of real number to the set of real number, you pick if you want to show that this is not one to one, if you have to show that g of x equal to x or x squared is not 1 to 1, what you can do is just have j of minus 1 equal to j of 1 equal to 1. So you can say that, but minus 1 is different than 1, because the definition of 1 to 1 function say that if you have j of x1 equal to j of x2, this implies x1 equal to x2. In this case, this function is not 1 to 1. The reason is we have indeed j of x1 equal to j of x2, but x1 and x2 are different. So this is true, we get this equality, but here if these elements are different, but indeed we get the same element output. So this is correct from this side, but this side is false. So this is not 1 to 1. So this for this case we show that it's not onto. So just forget about this proof that we did here, but at least you see what we are looking for. This was indeed in the set of integers, but we say that for all y. In this case we just find one y equal to 0, that failed, so it's not onto. And then to conclude the recitation of today, I'm going to take a look at some family of set. So this can also help you on your homework. If I give you the set, if I say that a k is let me just put 1, 2, 3, 4, 5, then I give you this set, the union of n equal to 1 up to k of 1 over n 1. So what is this set? So basically this set is, because the union of set is going to be 1 over 1 1 union 1 over 2 1 union 1 over 3 1 union 1 over 4 1 union 1 over 5 1, right? So that's the union of that set. So how can you find this set? What's this? So this equal to what? That's the question that we are asking here. So in order to find that is I'm going to draw this thing here. So this is 1. So this is like 0.5. This is 0.33. So this is like I think this is 0.25, and this is yeah, this is 0.2 something, close to that, 0.2. So if you draw this on the line, on the real line, so our line here is, this is 0. So the first set is just 1, but we exclude. This means we exclude. So this one is we exclude. So this is just 1. I just put 1 there. 1 exclude. So this is 1. And then the second set is 1/2 1. So basically this, I'm going to pick different color. For this set is 1/2 1. So it's something here. Again, we exclude this part. The second set is 1/3, 1/3, 1. So the second set is what we have here, this part. So let me use this color. So the second set is and then you exclude here. Let me just use the yellow color. Exclude there. And then the third set is this set. So it's going to be something. Let me just use that color there. It's going to be something like this. Right, exclude again. And the last set is going to be whatever you have here left. So it's going to be something here. It's going to be this. All right, something like that. And what you can see is the union of this set is what is going to be basically the union of this set is the union of all this. So we want something that cover all the set. So it's going to be all this part. So from here to this part, right? It's going to be this. And this last element is 1/5. So this union is basically this entire set, because the union, it was the intersection. You should think about something that's just this part, because you need something that cover all the set. So the intersection should be only this part. It was the intersection. It should be this, something that the intersection basically. So this, you can tell that from this expression what we just did here. The union of this set is going to be this part. So which is so this set gives us 1/5 because it's excluded 1, right? So that's the what we get from there. This is the union of this. So that's what we get from there. So that was, I was just trying to add this so you can understand how this stuff work. And if you have additional question, feel free to stop by the office hour so we can see if we can help. That's what I have for today, and thank you. Hopefully this will help for the homework and help you understand the concept that we have for this set of function, and maybe some extra stuff on set. And before we close, I want to emphasize on one more thing. When you have two set, when you have two set when you have two set A cross B, I gave you this last time, is a set of A, B, such that A is in A and B is in B. So this is A cross B. It's the same idea that if you want to prove that something if you have to prove that A union B cross something C is a subset of something, right? It's a subset of something. Because you have the cross product here, you cannot just pick one element like we usually put. You cannot say that just let A in A minus B cross C. You cannot pick A like this, because based on defining the cross product, you have it has to be pair of elements. So you cannot do this. This is not good. This is not going to be good. You cannot do this. But what you can do is you can say that let A be in A minus B cross C. So you can do this, because when you do this, it's going to be easier to extend, and from here, because the cross product, you whenever you see the cross product, you have to know how to pick the pair of elements. So this requires a pair of elements to be able to prove something. So in this case, you must show that you must assume from here, you assume that A had to be in A minus B, and B had to be in C. So that's the definition of cross product, and this is very useful because you are going to use that a lot in future proof. And also you had something like this on your homework, but I think few of you was able to handle it properly. So that's what I was about to add there. So whenever you have the cross product of two sets, you always want to make sure that you pick a pair of elements, not one single element. So this is not correct, but this is what you need in order to prove correctly. So that's what I have for today, and feel free to stop by the office hour if you have extra question. And also for this one, I explain you what you need here. This is the union of the set. In this case, in the case of your homework, you have the infinite, so it's going to be keep going. But what you observe here, as you go to infinity, as the number increase, this is going to go close to 0. So the limit as n goes to infinity of 1 over n is 0. So when n goes to infinity, this number tends to go close to 0. So that's going to be a hint too. So yeah, so the limit as n goes to infinity of 1 over n is 0. So when you go close to infinity, this number go close to 0. So you have to understand this concept. It's going to help you somehow. And you observe the pattern, what is going on here. It was, I said, it was the intersection. It should be this part, because we want the set something that cover all the set, so it should be this part if it was the intersection. But since it's the union, we have to pick something that the largest part of the set. So the union or the set gave you this. So that's what I have for today. And if you have additional question, stop by the office hour or email us. We try to our best to answer or to help. Thank you. Hopefully this helps. Thanks.